hand it over to the next speaker, Sophie Koudmani. It's going to talk about the supermassive black hole galaxy connection.
Okay. Yeah. Can you hear me okay with the mic? We have to a bit higher. All right. So yeah, first of all, thanks to the organizers for putting together this wonderful meeting. Actually my first time in California, and I'm loving it already. And yeah, so today I'm going to talk about my work on the supermassive black hole galaxy connection. And yeah, we've already had a few talks about this that have told us about the exciting recent developments. So in particular, these mysterious overmassive black holes that have been uncovered by JWST in the early universe. And now, of course, this could also be affected by selection effects, but nevertheless, the fact remains that for simulation, it is very difficult to reproduce this population. And there's also been another exciting recent discovery, which is a signal consistent with the gravitational wave background from supermassive black hole inspirals that was reported last summer from several pulsar timing array collaborations. And while the shape of the signal is consistent with the supermassive black hole inspiral hypothesis, the issue is that the signal seems to be too strong for what we would be predicting from the models. And these complications are likely to get only more complicated as we get more and more data in this now multi-messenger era of astrophysics. So with the launch of LISA in the 2030s, we will actually be able to map individual supermassive black hole merger events, which of course also closely relates to what Colin was talking about earlier. But why is it so difficult to get this right? I'm sure most of you are familiar with the fundamental issue that we are facing when modeling supermassive black holes and galaxy formations, which is the vast range of relevant scales. So if you were to simulate all of this ab initio, you would have to start at the event horizon, which for our Milky Way would be approximately microparsec scale. Then you would also need to model the scales of the accretion disk, which is where most of the feedback actually originates from. So the radiation, the jet is produced close to the inner edge of the disk. And then you of course also have this grid. Here we're talking then 10 milliparsecs. And then you want to know how do all of these different feedback processes couple to the inner region of the galaxy, which would be then at the scale of tens of parsecs. And then these feedback processes, as they couple, drive powerful outflows on the scales of tens of kiloparsecs, and these outflows then interact with inflows from the cosmic web. And of course, if you want to faithfully depict this cosmic web, you need the scales of tens of megaparsecs. So overall, we would need to spend at least 14 orders of magnitude, which is currently computationally infeasible and will remain so for the foreseeable future. But there are a few tricks that you can do to still study this, so you don't have to give up. But there are already some really impressive projects that say, okay, let's forget about all of the cosmic web stuff and let's just simulate idealized galaxies, and then you can have some boundary conditions that model these cosmic gas inflows. And then there are some simulations that from these idealized galaxy scales actually already push all the way down to very close to the event horizon. So that is one strategy you can take. The other strategy is that you say, okay, let's encapsulate everything that happens here at the small scales in a subgrid model. So we still have the cosmic web, the cosmological evolution of our universe, but everything that happens in the very center of the galaxy has to be described with the subgrid model. And indeed, that's the approach that most cosmological simulations necessarily take. And the model that is most popular for representing black hole growth in cosmological simulations is the Bondi accretion model. And this is mainly because it allows for a very convenient way of estimating the black hole growth rate. So I've given you here the Bondi formula. And what's most important is all you need is the black hole mass, the gas density, and the gas count. And for the Bondi formalism, you need to estimate this gas density and gas count speed at the scale of the Bondi radius, where you change to a free fall type solution. And this characteristic Bondi radius is typically 5 to 5,000 parsecs. This is kind of black holes. So this is already a whole lot better than microparsecs. Although it should be said that this Bondi radius is still quite often not resolved in cosmological simulations. And there are a bunch of other caveats when using the Bondi model. So there are several simplifying assumptions, mainly about the spherical symmetry assumption that is inherent to the Bondi derivation. So here on the left-hand side, you can see a typical Bondi flow, that assumes that the gases have been infalling in a spherically symmetric fashion, but obviously in a realistic galaxy situation, usually it's nothing like that. So you've got rotation, you've got outflows, all of these break the spherical symmetry, and then of course also quite often the gas transport is intrinsically linked to the angular momentum transport, which is neglected in the Bondi model. And another issue with Bondi is it's strong dependent on the black hole mass. So you can see here that the Bondi rate is proportional to the square of the black hole mass. This makes it very difficult to grow light seeds or to produce efficient AGN activity in dwarf galaxies. And this links back actually very nicely to Colin's talk that we just listened to, because there are already some deep X-ray surveys that allow you to constrain the AGN fraction in dwarf galaxies. So you have plotted the AGN fraction from observation here in yellow as a function of redshift. And if you look at cosmological simulations that use the Bondi models, for example here in Fable, you can see that these bright dwarf AGN at low redshift are completely absent from the simulation, so you can't get those. And then you have the related issue of also struggling to reproduce these very bright, very massive high redshift black holes, which were also mentioned by Roberto earlier. And this really matters. So I'm just going to give some very brief examples, given the limited time of this talk. But I've actually spent a lot of time working on AGN feedback in dwarf galaxies and modeling these processes. And you can see that once you depart from the traditional Bondi model, either by changing Bondi efficiency or by exploring gas supply limited models, you can get these very large-scale outflows which have a huge impact on the dwarf galaxies. And also I want to advertise a little ongoing project that I was working on at CCA with the FIRE people, where we looked at the impact of AGN feedback in dwarfs on dark matter distributions, and in particular in possibly explaining the puzzling diversity of dwarf galaxy rotation curves. And we find indeed that the addition of an AGN as well as a cosmic rays greatly increases the dwarf galaxy rotation curve diversity. And then finally getting back to JWST, is again, if you play with this accretion efficiency in the Bondi formula, so the so-called Bondi boost formalism, then you can actually reproduce these overmassive black holes from pretty much any peak mass. So this is pretty interesting that once you depart from this limiting traditional Bondi model, actually the field is wide open. So you can see this on the left-hand side. And if you look at some of the most extreme objects that were also discussed in previous talks, such as BNZ11 and the storm and overmassive black hole that was recently published, you can again see there's a wide range of tracks that match those, although it does seem that you may need superadding an accretion to fully match the properties of these objects, including star formation. But yeah, it is a bit unsatisfactory to just keep changing the boost factor in the Bondi formula and hoping for the best. So really what we want is a better formalism for black hole accretion and galaxy formation situations. And this is what I've been spending a lot of time working on recently. It's the so-called accretion disk particle method. And with this method, we don't just track the mass of the black hole particle, this is what's usually done in simulation, but we now also track the spin of the black hole particle, as well as the mass and the angular momentum of unresolved accretion disks surrounding the black hole. And the way that it usually works in practice is that you measure the mass fluxes and angular momentum fluxes in the very central region of the galaxy at the outer edge of the disk, so that you can be confident that both this mass and angular momentum will actually get added to the disk, and then you can forward model how the disk and the black hole are going to interact to evolve these 4 variables. And usually this is done with the Shakur-Zoniak spin-alpha disk. So there are various groups, I've put some examples up here that have explored this. And this is because the Shakur-Zoniak spin-alpha disk is the only global analytical accretion disk. But the issue is that the spin-alpha disk is only very valid in the high Eddington regime. Whereas if you go to lower Eddington ratios, you expect to transition to a thick accretion disk, and this transition could happen smoothly via a truncated disk. So you then have this truncated spin disk and inner hot flow that keeps expanding until it fully engulfs the outer spin disk, and then you have this pure hot thick accretion disk, which is often modeled via the ADA or ADIOS flow model. So in this paper that was recently accepted, we then extended the accretion disk particle method to be valid throughout all of these radiated regimes by tracking different disk states. And I told you, like, oh, there is no global analytical model, so the way we got around that is that we combined similar theory with CRI and HD simulations to parameterize the important quantities that these self-similar solutions break down, which is basically at the boundary. So in particular, in a disk set where the radiative efficiency is set, you cannot use the self-similar solutions anymore. So this is why then you go for fitting functions from highly accurate general relativistic radiation mechanism hydrodynamic simulations. And same to model the spin-up of the black hole as well as this. So I don't have a lot of time, but I will very quickly show you a first application of this model where we simulated supermassive black hole binaries. Again, they connect quite nicely to the talk we started off with this morning. And the exciting thing about supermassive black hole binaries is that this wide binary phase, so once they gravitate down to each other, but still at perturbations of tens of parsecs to the 1 parsec, is now in the reach of next generation radio facilities to be directly resolvable. And there are already some BLBI detections of the system. So we tested 2 different configurations. So first, a vanilla binary where you have an equal mass ratio and they're aligned, and we also tested non-equal mass ratios with aligned binaries. And the exciting thing is that when you compare this unified accretion disk model to the predictions from using a thin disk only model, as it has been done previously in the literature with the accretion disk particle method, the predictions for the electromagnetic counterparts of these binaries are vastly different. So you can see here in the top row the X-ray luminosity for the different binary setups, and the purple solid line is with the thin disk only model, and then the dashed dotted lines are the unified model, and the pink line also takes into account before. And perhaps unsurprisingly, with the unified model, these X-ray luminosities are a lot lower, and this is because with the unified model we tend to be in the truncated disk regime, so there's a hot flow in the center, and the radiative efficiency of that hot flow is a lot lower. But then you get the opposite situation when you look at the radioluminosity, because thick disks are much more efficient at jet production, partly because the jet then subtends a much smaller solid angle. So this means that with the unified accretion disk model, you get much brighter radio counterparts than with the thin disk only model. So yeah, vastly different electromagnetic counterparts with the more extended model. Okay, and I will only say one more thing, which is that the disk precession is also very, very different, and that means that the black hole spin evolution is completely different. It covers a much larger solid angle if you here compare the top panel against the bottom panel, and that then also means you would get more distributed feedback of the model. That's it. Thank you.
Okay, we have time for one question. Maybe next speaker could already come forward.
Very nice talk and an interesting talk. Maybe this is a very naive question. It's about what kind of interaction between this kind of new accretion mode and the accretion disk. So basically, the accretion rate from the disk model is a very important parameter to constrain the disk. So what kind of new things we know justify use this kind of, I think, non-boundary operation, and what kind of implication to the local universe, especially for the Milky Way and some massive galaxies we see?
This is a very good question. So in this paper, we have only tested these idealized scenarios, so either single supermassive black holes in gas clouds or the supermassive black hole binaries images. So no galaxy formation, full galaxy formation simulations yet, but this is what we're working on now. And it could basically go either way, right? It could seem both more efficient or less efficient with this model, so be a kind of bimodal outcome compared to one. Yeah, the issue is that you need very high resolution with this model. So you can use it in cosmological zoom-in simulations if you need to resolve down to the outer edge of the accretion disk. But in large cosmological volumes, if you are probably interested in statistical predictions, there needs to be an extra step, which is post-grading this model. And this is probably relevant for the afternoon session when thinking about combining simulations and machine learning. But yeah, this would now lead to a whole different discussion.
Okay, thank you, Sophie.